Hi, all. Hopefully, everybody's staying safe and healthy. I am Maggie from MIT, and I am presenting joint work that I've done with Frederick Johansson, John Guttag, and David Sontag. In this work, we study how we can build models to inform good decision making. Consider, for example, a physician who was trying to decide whether or not to administer a certain treatment to her patient. This treatment may or may not extend her patient's life. What she really wants to know is what would happen to her patient if she gets assigned the treatment or if she does not. And we refer to these kind of outcomes as counterfactual outcomes, and we use capital Ys to denote them with a subscript of the treatment assignment. Now, these are different from knowing what happened to patients who were assigned the treatment in an observational data where the treatment assignment is biased. These are conditionals and encode associations, and we will use small y's to denote them. Now, in order to make reliable decisions, we need to build models that learn something about the counterfactual outcomes. Nobody explains better why we need counterfactual reasoning for reliable interventions better than underappreciated scholar and star basketball player Steph Curry. So I'm going to let him explain why.
New degree dry spray is a game changer, but will it make you better at basketball? We decided to put it to the test. You ready? It's got to be the dry spray.
So you can imagine the kind of frustration that would come with doing an intervention, like buying degree dry spray and still not being able to shoot perfect three-pointers like Curry. That's the kind of thing that might happen if we rely on non-causal models, which encode associations, and that is really the reason why we need counterfactuals or causal reasoning for reliable interventions. Now, hopefully at this point, Steph Curry has managed to convince everybody that we need causal reasoning for reliable interventions. And now the question becomes, do we really need exact causal estimates to inform reliable decisions? And the answer is sometimes no. Let's look back at the example of the physician who's trying to decide whether or not to treat her patient. In this situation, asking models to make statements like, the treatment will cause the life expectancy to increase by 4 years, 6 months, 11 days, and 2 hours is an overkill. And it's often sufficient to say that the treatment will increase life expectancy by 4 to 5 years. And this is the main intuition behind our work, that in some cases, a rough estimate of the causal effect is enough. So in this paper, we seek to build models that enable us to make statements such as the following. If treated, the patient's life expectancy will be 80 to 85 years. If not treated, it will be 70 to 75 years. Now let's break down the statement a little bit to try to get a concrete learning objective. We have that each patient has an observed set of characteristics, X, and we want to make inferences about his life expectancy, for example, under treatment. We want to say there will be roughly 80 to 85 years. Let's take the first value, 80 years. This will be the output of a learned function, and we will use an F with a subscript L to denote the lower bound and a superscript of 1 to denote the treatment assignment or the treatment value. This is only one of the functions that we want to learn, because we also want to learn the upper estimate or the upper bound for the patient's outcome if he is treated. And similarly, we want to learn the lower and upper bound estimates for the outcome under non-treatment. Now, how are we going to get these estimates? First, we are going to make a set of usual assumptions that enable us to use observed data where the treatment assignment is biased to make causal statements. And these three assumptions are strong ignorability, overlap, and consistency. I'm happy to discuss these further in the question and answer session. Now, these assumptions don't completely solve our problem because even if we have the counterfactual labels, minimizing the mean squared error, which we typically do in machine learning, would be implicitly shooting to get the most accurate estimate. And we've already established that the most accurate estimate might be an overkill. So instead, we require that these 4 functions correctly cover the true outcomes, or in other words, they have a low false coverage rate, meaning that the true counterfactual outcome is never lower than the lower bound or higher than the upper bound. So this means that our metric of interest will be to achieve a low false coverage rate, meaning the probability the true counterfactual does not fall within this estimated interval is less than some small tolerance parameter rho. So our learning objective will be to learn meaningful upper and lower bound functions such that the false coverage rate does not exceed a pre-specified rho. And for a second, we will set aside what makes a bound meaningful We'll get back to it later, but we will focus on finding bounds that achieve a good false coverage rate, or FCR. On a very intuitive level, our theory suggests that in most cases, just estimating a lower and upper bound function is easier than the task of estimating the true function. Consider the illustration on the slide. Here we have that the x-axis is the patient age, and the dotted gray line shows the true function, and the shaded region shows noise around the true values. Now, while the true function looks like it is hard to learn, we can use simple straight lines to perfectly cover the counterfactual outcomes. Now, because the arguments are all symmetric with respect to the upper and lower bounds, let's look for a bit with a bit more detail at how hard it is to get a lower bound to keep things simple. Here, the generalization risk, which we denote by R, is defined as the probability of observing a patient that is outside the training data, such that the estimated lower bound is higher than the true counterfactual outcome under treatment T. Now, let's say we want to be extra cautious, and not only do we want the lower bound to correctly bound the data, but we also want it to bound the data with some buffer region or some margin. And that margin we will call gamma. We'll give it the name gamma. And we'll redefine the risk to include and depend on this gamma. This gamma will play an important role in our theoretical analysis. It can be viewed as a measure of confidence. The larger the gamma, the more confident we are that we accurately bound the observed outcomes. We may require that the observed points in the training data all be correctly bounded, or we can allow for some violations, such as these like 3 scattered points, which are clearly violating the lower bound. Now, what we find is that for every value of gamma, and for an observed data set of size n, the risk of overestimation of the outcome under some treatment T is bounded above by this term that you see on the slide. There are 2 relatively unusual or interesting terms in this bound. The first is just a measure of how biased the treatment assignment is. The larger it is, the worse off we are. And it usually appears when we are doing causal inference in finite sample settings. The other interesting term is K, and K has 2 parts. The first measures the complexity of the learning task, and it is controlled by gamma. The larger the gamma is, the smaller this term is, and the smaller our risk is. Meaning when we demand higher confidence, this term becomes smaller. The second term is the sum of the magnitude of the violations on the training data, which also decreases as gamma increases. Now, the important takeaway here is that the generalization error is controlled by the margin parameter gamma and does not depend on the true complexity of the function class to which the counterfactual outcomes belong. We can now go back to something that we set aside a second ago, which is what does it mean to have meaningful bounds? Let's consider those 2 examples on the slide. These 2 bounds perfectly cover the data, and thus far our analysis does not indicate which one of them is optimal. And if you feel like you know which one is better, I encourage you to shout that answer out loud wherever you are. Now, the reality is this is a bit of a trick question. The optimal estimates can vary on an application-by-application basis. For example, the bounds in A give the tightest intervals on average, but you might notice that they are wider for younger people as compared to older people. In B, we make sure that the bounds are never too wide for a single group, and we get the same width of intervals independent of age, so you can think about this as a more fair or equitable objective. Now, ideally, our approach would be flexible enough to incorporate these different possible objectives. And this brings us to our suggested approach. In our suggested approach, we maximize some utility function f, or some utility function that is defined with respect to the learned bounds f, while enforcing the required false coverage rate as a constraint. We can plug in different utility functions depending on the type of application. So for example, we can make sure that the worst case interval is never too wide by minimizing the maximum interval width. We can also minimize the average interval width by minimizing the squared differences between the upper and lower bounds as weighted by the inverse propensity score. In our paper, we also show that when we use absolute rather than squared differences, we recover the quantile regression for small enough required false coverage rates. Now, to test the performance of our model, we use semi-simulated data. Specifically, we use a challenge data set from the Atlantic Causal Inference Challenge, or ACIC, where X is extracted from the real data, but the treatment assignment and the outcomes are both simulated. And this allows us to test the performance of our model on simulated ground truth. For this experiment, we will focus on getting the tightest intervals on average. However, in the paper, we sort of like discuss other possible utilities. And here we will set the false coverage rate or the required false coverage rate to be some value, and we will look at the violations with respect to this required false coverage rate, and we will look at the mean interval width. Now on this plot, you see on the x-axis we have the achieved false coverage rate, and on the y-axis we have the mean interval width. And the dotted line here shows the required false coverage rate. So the models to the left of the dotted line are the ones which do not violate the required false coverage rate, so they are good. We compare our model against several benchmarks, and there are more benchmarks in the paper, but here we're showing a kernel regression where the upper and lower bounds are estimated using conformal intervals, which are conformal intervals are similar to confidence intervals, but they have been shown to perform better in finite samples. We also compare against Bayesian additive regression trees, or BART. But what we see here is that the only model that does not violate the required false coverage rate is ours. And it does so by fitting simpler functions that correctly bound the outcomes, unlike the two baselines, which essentially fit the hard function and then shift it up and down by some factor to get the final bounds. In other words, our model is able to leverage the fact that there might be simpler functions that achieve good false coverage rate. In fact, we see that this holds for all required false coverage rates. The plot on the right shows the achieved false coverage rate on the x-axis and the mean interval width on the y-axis. We see that our model and BART roughly have the same mean interval width for all values of the achieved false coverage rate. But on the left, we show the plot shows on the x-axis the required false coverage rate, and on the y-axis we have the achieved minus the required false coverage rate. So models above the dotted line are violating the required false coverage rate, and we see that our model consistently gives lower violations than the baselines. Now this implies that while BART achieves a similar mean interval width to our model, it does so at the cost of a higher violation to the required false coverage rate, which again happens because the baselines are implicitly aiming to get the most accurate estimates and not the ones that ensure good coverage of the potential outcomes. Now, in summary, we showed that estimating intervals for causal effects is often easier than getting the exact estimates, and we proposed an approach to find meaningful bounds that do not violate a pre-specified false coverage rate. Additional both empirical and theoretical results are available in our paper, and please stop by the question and answer session if you have any questions. Thank you, and stay safe.